a couple of homework assignments by now. And we'll just start by taking some questions from those things. Mia? Okay. So looking at number 11, notice the directions here don't ask us to do this any particular way. So like you could just graph this and look at the picture and do that. That's fine. I'm assuming that you're trying to do it algebraically and want to ask about that, which is fine also. So this one is a little bit different than the ones that we saw in the examples. And I'll explain why in a moment. We'd start it the same way though. The domain for this should be easy to see that it's all real numbers. Obviously that's the implicit domain when you start, and the only operations going on were squaring and subtraction, which don't affect real numbers in a way that can give you a problem. So then we're going to go and we're going to look at the function and decide if the intervals that are increasing and decreasing, or see if the function's all one or the other. This one in particular is not, just one. So the graph of it's going to look something like this. Oops, sorry. Wrong way. Something like this. So we are decreasing from negative infinity to 0, and then we're increasing from 0 to positive infinity, right? Okay, so if I want to do my range then, I'm going to look at the lower bound and upper bound for each of these, and then I'll take the overlap of those. Or really I'll take the lowest of the lowest and the highest of the highest. In this case it doesn't really make much difference though. So I'm going to say lower bound for the decreasing. So because it's decreasing, I know I'm going to be flipping. And the upper bound for the decreasing. So f of 0 is just -4. That's easy, right? And f of infinity is still going to be infinity, right? Infinity squared minus 4 is still infinity. And because this is an upper bound, I know that's going to be a positive infinity. And then for my increasing, I don't switch the bounds. So increasing is going to be f of 0, which we just saw was -4. And the lower bound for the increasing is going to be f of infinity, which again is positive infinity. And so if I look at my lower bounds, they're both the same. So no issue there. And the upper bounds are both the same. If they were different, you take the lowest of the lower bound. Or if the upper bounds are different, you take the highest of the upper bounds. And we know the parenthesis always goes on the infinity. Now the -4, we're going to notice -4 is in my domain. So, I'm sorry, the 0, I guess, that the -4 came from is in the domain. So that's why the -4 is getting a bracket. Well, 0 is the x that gives me that particular y, right? 0's in the real numbers. So 0, there's a point when x equals 0. The y coordinate is -4. It's included, right? Yeah, any follow-ups on 11 before we move forward? Max?
So for the upper bound and decreasing, why would it be negative infinity? You're taking it from decreasing.
So the negative and positive infinities are no way tied to the sign of the infinities at the start. It's only tied to the upper, whether it's an upper bound or lower bound. So upper bounds, if you get an infinity, it's always a positive infinity. And for the lower bounds, if you get infinity, it's always a negative infinity. Mia?
So if you always have negative
No, not necessarily. So like if this was just like y equals x, that domain is all real numbers, but it's increasing the whole time, so there's nothing to split. It's only if you have a function that like changes from increasing to decreasing or whatever that you could run into trouble. Is that okay? Okay. Okay, and then Paul, you want to talk about 8, you said?
Yeah.
Okay. So what is that? K of x equals x over x squared minus 1. So again, the implicit or the implied domain is all real numbers because there's no context to this problem. The relevant domain, then, we look at the operations involved. I see squaring, I see subtraction, I see division. The only of those that can cause an issue for us is the division. So I know I'm going to set the denominator not equal to 0. And then if I solve that, I could factor that to solve that quadratic, I guess. You could do a variety of things. Oops, should be not equal to 0. So I get x is not equal to 1 and x is not equal to -1, right? Now, instead of splitting each of these into inequalities, I'm just going to think about what this is really saying, and then I'm going to write my inequalities from that. So x cannot equal -1, and x cannot equal +1. So I can have x's that are less than -1. I can have x's in between -1 and +1. Or I could have x's that are bigger than 1. Right? That'll cover all the x's that aren't equal -1 or +1. So I can then just create an interval for each of these. So less than -1 is -infinity to -1. Between -1 and +1 is just -1 to +1. And then greater than +1 is just 1 to infinity. And I'm done. Joe?
So, where is the negative infinity coming from? Is it just like...
Well, the numbers that are less than -1 would be like -2, -3, -4, and continuing down forever.
Right.
So the smallest number that's less than -1 is -infinity.
Yeah.
Okay. So again, like if you're not sure, just like think about the numbers, like what the inequality is really saying, what numbers would be included in that. Just usually get a good picture of what to do. Paul?
So like, there's x over x squared minus 1. What happens to the x on top? Like, why did we do that?
Because the numerator of a fraction can't cause the thing to become undefined, right?
So, I'm just like,
Yeah. Yeah. Just like we, like in the previous problem when we did the domain, we ignored this x squared minus 4 altogether because squaring and subtraction didn't really do anything, Mackenzie? 12. Okay. So again, the domain here is going to be the place where the square root is non-negative. So 3 to positive infinity. I shortcutted through some steps there. Is that okay with you, Mackenzie? Okay. And then if I look at the graph of this, it's going to look something like that. So it's easy to see this is increasing over its entire domain, right? So for my range, my lower bound is just for the range is going to be f of the lower bound from the domain. Since it's increasing, they just match up. So that's f of 3. So that just is 2. And the upper bound for the range is going to be f of the upper bound for the domain. So f of positive infinity, which is still going to be infinity. And because this is an upper bound, it'll be positive infinity. So my range, h of x, will be a member of the set from 2 to positive infinity. The question becomes, is 2 getting a bracket or a parenthesis? Since my y-coordinate of 2 comes from the x-coordinate 3, and 3 is included in the domain, 2 should also be included in the range. And that's it. Mackenzie? So to explain the difference between them? So it matters where the function is increasing and decreasing. If you're talking about a function that's increasing, lower goes to lower and upper goes to upper. If it's decreasing, they switch. So, and if it's decreasing, the lower bound for the range comes from the upper bound of the domain, and the upper bound of the range comes from the lower bound of the domain. That's what you're asking? So that's why on number 11, if you look here on the decreasing one, that's what we're seeing, right? Is the upper bound went to the lower, was used for the lower bound, and the lower bound was used for the upper bound. Cool? Okay. Paul?
Number 8. I mean 10.
Sure. So again, the implicit domain is all real numbers. If I look at what's going on, though, I see I have subtraction, who cares? Division, well, that's an issue. So the division, I know the denominator cannot equal 0. And I have a square root, and I know that the stuff under the square root has to be non-negative. Now, to solve square root of x is equal to 0, I can square both sides and say x is not equal to 0. And then my suggestion here would be I'm going to just combine these two into a single inequality. Because if I have x cannot equal 0, or x can be greater than or equal to 0. Really, if I combine these together, I just have x is greater than 0, right? And so from there, my interval is really easy. And I'm done. Hi. How are you?
Good, how are you?
I'm okay. Sienna. Looks like you're leaving early today. Good for you. Does that feel okay? Any more questions for me? Okay, Alexis. 15. So this is one that's just done all on our calculator. So I'm probably not going to write anything down. We'll just run through it on the calculator. So I'll go to the y equals, and I'm going to type in what we got here, just exactly as it looks on my calculator, or on my piece of paper. Okay. And then I'm going to do zoom standard because I'm pretty sure that I was messing around with my windows in a previous section. So there's my graph. When I look at this graph, I see one local maximum and one local minimum. I'm going to find that local maximum first by pressing second and then the trace button. From that menu, I'm going to choose the maximum command. The calculator is going to ask me 3 questions: left bound, right bound, and guess. So left bound, I'm going to give it a point that is on like this part of the graph, somewhere over here. I'll just move my cursor over there. That looks good. I'll press enter. And then for the right bound, it's going to move somewhere over here on this little section. So I'll just do that. That looks good. I'll press enter. The guess doesn't matter. So there we go. For 2 decimal places, I would call that negative 0.09, comma 2.05. Then to find the minimum, I'm just going to repeat that same process. So I'm going to press second and trace, but this time choose the minimum command. My left bound is going to be somewhere in this little section here. Move my cursor, press enter. My right bound is going to be somewhere over here. Move my cursor, and then do my guess. So the minimum there would be like 1.20, comma, negative 1.22. Does that feel okay, Alexis? You're welcome. Grace. 21? Sure. So here we're trying to determine whether something is odd or even or neither. So the first step is to compute g of negative x. So that's going to give me 1 over negative x. And I remember with a fraction, I can take that negative sign and kind of move it wherever I want to. So instead of putting it in the denominator, I'm just going to put it out front. And 1 over x is exactly what g of x was. So I have, in fact, negative 1 over x is negative g of x. So this thing is odd. And I'm done. Yes, Paul?
So if you had like number 19 is like negative 2x to the 4th, that would be even because you're just kind of solving in your head, right?
Well, you'd have it's asking you to like support your answer algebraically, so you should be writing some stuff down like we did here.
Could you do that one? Just see what we do.
I mean, like the same thing, right? Plug negative x in. Negative x to the fourth is just x to the fourth, which is f of x. So it's even.
Okay, so it's like a direct.
Yep.
Okay. Why do you have to make it a negative?
So we talked about last time the definitions of odd, even, and neither. So if we go back, oh, I'm in the wrong notebook. That's what's going on. Anyways, here, it's fine. I don't know where it's at here. There we go. So when we defined odd, even, and neither, those are our definitions. So notice each definition starts with f of negative x. So I'm just using that definition to do my proof. Is that okay? What is going on? Oh boy, oh boy, oh boy. Okay. Got all flustered here. Okay. Sorry, who's next? Anybody? Mia?
So if it's asking for the algorithm,
No. No. There's really nothing to do there. Tyler? Yep. So this is all on your calculator. So we'll go with the y equals menu, clear out anything you might have had there, and then we'll just type in our function. So I have x times, and then to get the absolute value, we'll press the math button and go over to the number menu. And that first command there is the ABS. So 2x minus 1. And then let's go ahead and hit graph. So if I look at this initially, it doesn't look like anything's going on, which seems odd considering that the problem is asking for maxima and minima, that I don't see any there. So my suspicion is somewhere here where it looks like it flattens out for just a minute, there might be a little doo-doop or something in there. I'm just going to have to zoom in to take a closer look. So it looks like everything I might be interested in would be between like -1 and +1. So you could use the zoom in command, or you could just pick a custom window. I'm going to pick a custom window because I feel like I'm smarter than my calculator is and feel comfortable doing that. So I'm just picking from -1 to +1 on both the x's and y's. And if I do that, I do indeed see a maximum and minimum snuck in there. Mr. Kulik, you cheeky guy. So I have a maximum here and a minimum here. And I can find them the same way that we did for Alexis's one. So second, trace, I'll do the maximum first. Left bound, that spot is good. right bound, I'll move over here to the right side of it. Press enter, guess is fine. So I have 0.25, comma 0.13, I guess, to 2 decimal places. And then we'll do the minimum, so second trace. This time I'll pick a minimum. That's good for left bound. Right bound, that looks good. Press enter again. I have 0.5, and then really this is 0, right? 3.0799 (-7). That capital letter E is what? Yeah, scientific notation. So this is like a decimal point, 6 zeros, and then that decimal, which rounded to 2 decimal places, is 0. FYI, depending on like what you did, you may end up with like a different number in scientific notation, but the point is that it'll be something that's real small and real close to 0, that to 2 decimal places is 0. It might disagree with what I have here. It has to do with like the approximation algorithm that the calculator is using to do this, because it's not actually doing the calculus to get the solution. It's doing like an approximation thing, and it's probably set up where like after so many passes through, it just stops, and whatever's left is what it's calling it. Really, the maximum is 0.5 and 0, or I'm sorry, the local minimum is 0.5 and 0, rather than like what it's given me here. But the algorithm is one of those things where like it's possible maybe it doesn't even terminate. Like it's possible it could run infinitely and like crash your calculator. So it probably has like an automatic shut off, like after so long of running it just stops, or so many cycles through it just stops, and whatever's left it's saying, okay, that's close enough. I don't know enough about how it's actually programmed to say for sure, but that's my suspicion when I see an output like this. Anybody else? Okay. So, we guys hopefully remember the definition of an asymptote from last year in our Algebra 2 course. So we defined an asymptote there rather informally, just as a line that a graph approaches but never crosses or touches. And if you remember from your Algebra 2 class last year, we talked often about vertical asymptotes and horizontal asymptotes, and maybe even briefly about oblique or slant asymptotes. So let's look at a quick example, and I'm going to generate this example digitally, so we have a nice picture of what's going on, because, well, my penmanship skills sometimes leave something to be desired, and I just want to try to do a nice job sometimes. You know, sometimes a sketch is good enough, and sometimes it's not, you know what I mean? You guys get it, right? You've seen enough of my writing by now to go and see that. All right. That looks good. Hey. Okay. So let's say we have a function that whose graph looks like this. And we're just taking a peep at it. So it looks like I have a vertical asymptote here at, say, -3. You guys buy that? Looks like I have another one here at +1. And it looks like I have another maybe horizontal asymptote here also at +1. Now, that horizontal asymptote, should I technically be calling that an asymptote? Why not? Yeah, like it's in the middle. It crosses somewhere in the middle there, right? You see the graph crossing that what I just referred to as a horizontal asymptote. So technically it's not. The weaker condition for something like this, where it's like almost like an asymptote, because we have the approaches part, that part of the definition is being held, but the crossing, we're kind of failing on that. We call these things end behaviors, which is like the more generic term. You know, like mammal is more generic than dog is. Like a dog is a more specific kind of mammal than just like a mammal. A horizontal asymptote is more specific than an end behavior. We're not going to worry too much about that distinction right now in this chapter, and I'm just going to call these things horizontal asymptotes for right now, even if they're not actually asymptotes right now. But I know at least in my Algebra 2 class, we talk about that distinction. I want to make sure that I advertise that we are going to be a little glib with that definition of a horizontal asymptote in particular right now. And we'll tighten that up a little bit later as we go. But before anybody starts losing their stuff about like, whoa. It's like, I know. So the one of the common function types that we saw that often will have these vertical and horizontal asymptotes are these rational functions. So the graph of what you're looking at above, or this is the function belonging to that graph above, I guess is the way to say that. Do you remember how to find the vertical asymptotes for a rational function like this? Paul? It's not the x's, Mia? The denominator, yeah. So to get those vertical asymptotes, and I want to add in one little condition there, Mia, is that we should set the reduced denominator equal to 0 to get the vertical asymptotes, because it's possible that like you might have found like a removable discontinuity instead of an asymptote, but in this case it doesn't matter, because if you look at the numerator, that thing isn't going to factor, right? There's not two things that multiply to give you -3 and add to give you +3. So there's no reducing that can happen. So just in this case, denominator set equal to 0 is going to be fine. But in general, you want to at least make a cursory glance to see if there's any reducing you can do. So if I solve this, factoring seems to be the easiest way to do that. And I get my asymptotes at -3 and +1. Which matches what we observe from the picture, right? Does that all ring a bell? Yep. Okay. Do you remember how we found the horizontal asymptotes for something like this last year? Ella? So if we set y to 0, what we're going to find are the x-intercepts, right? So if you remember, and I'm not saying that you even needed to, oh, Grace. So you're quite close, okay? So yeah, there's like a couple of different cases. In fact, there's 3 cases. What you have to compare is the degrees of the numerator with the degrees of the denominator, and like, you know, sometimes it's 0, sometimes it's a constant, sometimes it's an oblique asymptote. It's just kind of a mess. We're not going to worry about that so much right now. What we're going to do is just kind of worry about this, confirming these horizontal asymptotes numerically. So what I'm going to do is I'm just going to use my calculator here. I'm going to type in my function. I'm going to make sure that I put parentheses around the entire numerator and the entire denominator. And then I'm going to graph this on the window from negative 1,000 to positive 1,000. Oops. Probably go up by hundreds just so I have some tick marks there to add a little sense of scale. And then I'm just going to hit graph. Hold on a second. Oh, yeah, sure, whatever. Let's not do the y's. Let's just leave the y's the way they were. I'm silly. So I get this boring looking thing that looks like a straight line. Now I know it's not actually a straight line, but because of how far I'm zoomed out on the x, it's just going to appear to be a straight line. What I'm going to do is I'm going to check to make sure that that asymptotic behavior that it appears that it has, where I'm getting like it looking like the graph looking like a straight line, that I can observe that on the left side and the right side. So what I'm going to do is I'm just going to look at some specific values of my function, and for some specific x's getting progressively larger. And see if both ends of my graph, like the asymptote, kind of agrees. So I'm going to press second and the trace button, and this time I'm going to choose the value command. And what this allows me to do is pick a value of x, and if I press enter, it's going to find that, or give me the y coordinate for that, the point that has that x value. So what do we got? We got 1.085 or something there. So do that for 10, and I'll just repeat, and I'll do it for 100. What do we got? 1.009. And do it again for 1,000. And I got 1.000. But what I'm seeing here is that the bigger the x is getting, the closer we're getting to 1 from above, right? At no point were we below 1 and then back above 1. We're all on one side of that line y equals 1. Joe?
So, give me an error.
That's probably because you're picking up an x value that's not on your graph.
Also, I see like shown.
Yeah, so you have to be able to see the x value. Your calculator, did you give you a window dimension error or something?
Yeah.
So if I picked like 1001, remember I picked my window from negative 1000 to positive 1000?
Yeah.
It gives me an invalid error because I'm picking an x coordinate that's not on my picture. Grace. Of course. You're welcome. And now I'm going to do the same thing with the negatives and see if those are also heading towards 1. So I'll do negative 10. So I have 0.870 there. And then negative 100. I got 0.989 there. And then, oops, these are supposed to be thousands. I don't know why I wrote hundreds there. Oops-a-doops. I typed in hundreds or thousands. Now I'm saying it. And that's 0.999 there. So again, as my x's are getting smaller, I'm getting closer to 1 from below, right? So at this point, I'm pretty satisfied that 1 is my asymptote, and that's it. Okay? When we go back and talk again about rational functions later on, we'll review those rules specific to rational functions. But this approach that we're giving you works in general for any kind of horizontal asymptote you might be interested in, right? We're just going to numerically approximate it by getting progressively bigger and smaller x values and make sure that things appear to be doing what we think they're doing. Is that okay? All right. The next thing that we'll talk about here is function operations. And so there are 4 basic function operations that we would have learned. Well, they're just like the analogs of the 4 basic operations we learned in elementary school. So let f and g be 2 functions with intersecting domains. Then, for all values of x, in that intersection of domains, the operations on f and g are defined. Got the sum operation that says the function f plus g of x. Well, that's easy to evaluate. We're just going to do f at the function x plus, or f at the value x plus g at the value x. It's going to give us the same thing. And difference f minus g evaluated at x is just f of x minus g of x. There's product. So f times g evaluated at x is just f of x times g of x. and quotient. So f divided by g evaluated at x is f of x divided by g of x, given that g of x is non-zero. Difference. So in this preamble here, it says f and g be two functions with intersecting domains. Why do they have to have intersecting domains? So the start of our definition here says let f and g be two functions with intersecting domains. Why do we need that intersecting domain part? Well, imagine that we have like f of x is the square root of x minus 2, and then g of x is the square root of, let's say, 1 minus x. The domain here is the x's that are greater than or equal to 2. Actually, just write as an inequality. And the x's here are the x's that are less than or equal to 1. Is there anything in common between these two functions? Is there any x's in common? Well, x is greater than or equal to 2. So there's no x's in common, right? So if I wanted to do like, f plus g of 3, well, that's not equal to f of 3 plus g of 3 because this part is undefined. You know what I mean? If there's no x's in common, then we can't actually perform any of these operations because one of the two functions is going to be undefined no matter what we do.
Wait, why is it?
Well, yeah, I mean, if I do 1 minus 3, it's a negative, and I take the square root of it, it's uh-oh. You know what I mean?
Yeah.
So just like if you don't have an x that you can plug into both functions that works for both of them, like what are we doing here? It's just, just making sure that like the problem's even possible. You know what I mean? So that's why that little caveat's in there. Okay. So let's look at a couple of examples here. So let's say my f of x is this function 2x minus 3. Let's say g of x is this function square root of x plus 2. And let's kind of evaluate some of these operations. So let's say I want to do f plus g of x. From our definition above, that's just the same thing as f of x plus g of x, right? And I know f of x is 2x minus 3. And g of x is square root of x plus 2. And can I do any more simplifying from that? What do you guys think? Can I combine any like terms here? Can I do with anything else? Sure.
Looks like there's an I.
That's a semicolon, homeboy. It's a semicolon. That's okay. Does that make it more semicolon-y?
Yeah, kind of a J now.
Oh my goodness. How about that?
Going.
No, I'd like to stop. So no, right? There's no like terms to combine at this point. There's nothing to, you can't put stuff that's outside a radical inside of a radical. We're done, right? Everybody's good? What if we did g minus f of x? Well, using our definition from above, that's going to be the same thing as g of x minus f of x. So that's x plus 2 minus 2x minus 3. Is that right? You should all have a big problem with what I've just written.
Domain, so.
No, nothing to do with not the domain that's a problem. Mia? Yeah, so Mia says it should be plus 3. The reason that is we're subtracting all of f of x. So I need to make sure that I'm distributing that negative through. So just a little algebra arithmetic error there where we forgot. Easy to make that mistake, which is why I'm highlighting it here. One of the more common mistakes I see students make in these kinds of algebra-ish classes is just getting a little bit sloppy with, our negative signs and parentheses and forgetting like, oh, negative of f of x. I just write down f of x and put a negative sign in front of it. It's like, oh, no, no, no. That negative sign needs to apply all of f of x. All right, let's say we have g times g of x. Well, that's g of x times g of x. Well, I was supposed to change colors there, huh? So you can see the difference between the problem and the work. And that's going to be square root x plus 2 times square root x plus 2. And what is the square root of x plus 2 times square root of x plus 2? Can we simplify that at all? What does it simplify to? Yeah, so that's like square root x plus 2 squared. And I know squares cancel square roots. So it's really this, right? Now, super technically speaking, we should really have an absolute value around that. Well, if I take something and square it, I get a positive thing. And then I square root it, still positive. So whatever's coming out of this should have to be a positive value. Now, it's not really necessary to do that because if I think back, if x plus 2 gave me something negative, we couldn't have taken the square root of it anyways. So like in this case, it's not really necessary that those absolute values are in there. But it wouldn't be wrong to include them either. Now let's do f divided by g of x. So that's going to be f of x divided by g of x. So that's 2x minus 3 over square root x plus 2. Any simplifying you guys want to do there? Anybody want to rationalize that denominator? Probably that fits with what we've been told, right? Is to do something like this. Who thinks that actually makes anything simpler?
No.
No, right? So one of the dirty little secrets that you're going to learn is that in high school you're told that like we need to rationalize all your denominators. By the time you get to like a Calc 2 or Calc 3 class, your professor's going to be like, stop rationalizing the denominators, you're just making things worse. Which is lovely to get like that mixed message, but like that's what happens. So we'll pick this up next time. I have put the assignment for the next homework check started, including everything from section 1.7. We have a lot left to do in 1.7, so it's looks pretty big to start with. I'd start on that now. You're able to do let's see. You'd be able to do like up through I guess not really that much of it because it's asking for composition right away. Anyways, I'll put all of the homework check through section 7 up on My Notre Dame, so if you wanted to start on things, you can start on it. We'll see you guys later, though. Have a good day.
For the homework quiz, are there partial points? I completely forgot.